Très bien, mais je vous propose de commencer le séminaire. Donc le séminaire d'aujourd'hui sera en anglais. So I will switch to English now. And so it's my pleasure to welcome Dreyer as our speaker today. So Dreyer is a senior research scientist at the Max Planck Institute for Software Systems in Germany, and also a professor at the University of Saarland in Saarbrücken. So he's an expert in functional programming languages and type systems. In particular, his PhD work was on the standard ML module system, and some of his postdoctoral work was on semantics of higher order, functional languages with imperative features, basically, a higher order store. And what he's been doing lately, and what he will talk about today, is to work on the Rust functional programming, the Rust systems programming language. So it's not at all a functional language in the sense that it's much lower level. In particular, you do all sorts of explicit management of memory and low-level shared memory concurrency. Yet it's a language that has a very powerful type system, extremely interesting design. And so Derek and his team, in the context of his ERC project, Rustbelt, has been working on better understanding of the Rust programming language, his type system, how to reason about programs, and that also led them to develop an extremely powerful program logic called Iris. Which is, I think he will say a few words about that, but kind of the ultimate concurrent separation logic as available today. So, thank you, Derek.
Thank you, Xavier. Can everyone hear me? Yes, good, great. Thank you very much for that lovely introduction, and thanks for inviting me to the Collège de France. Today I'm going to be talking, as Xavier said, about Rust and the work that we've been doing in the past 5 years or so on understanding and evolving this very interesting language. So for me, one of the reasons this is so exciting is that for a long time I was under the impression that there was only basically two kinds of work on programming languages. You could either work on languages that were kind of beautiful and well-designed and elegant, and where you were very excited to work on the language. So I'm thinking of languages like OCaml, for example, or Haskell, or many of these functional languages that Xavier has just been talking about. But to be honest, there's relatively few programmers who use these languages compared to the other type of language you could be working on, like JavaScript or PHP, or one of these languages that has massive user base but is a terrible language. And so I always thought, there was these two options. Either you do the thing, for beauty, or you do the thing that has sort of mass impact. And I think Rust is, what's interesting about Rust is it's somewhere in the middle. It's definitely not as popular as these terrible languages, but it does have, it is very well put together, it's very well thought through, and it's exploring a really novel point in the design space of programming languages. And furthermore, the designers of this language really appreciate interacting with academics, and they actually have a lot to there's a lot to be gained from the interaction between the developers of the language and academic researchers, and that's what I'll be talking about today. So how many of you, just to get a sense of the audience, how many of you have actually heard of the Rust programming language? Okay, quite a few, not everyone. And how many have actually programmed in Rust? Okay, not too bad. A few, that's good. So that's fine. If you've never heard of Rust, if you've never programmed in Rust, that's perfectly okay. I'm going to give you some background on what Rust is and try to give you an idea of what's interesting about this language. If you have programmed in Rust, that's also okay. There's only going to be about 10, 15 minutes of sort of review of the background, and then we'll get into the research questions. So what is Rust? Okay, so basically Rust is intended as a safe replacement for a language like C or C++. It's intended as a safe systems programming language. So what does that mean? It means a couple things. So one is it has support for low-level control over layout of data and management of resources in the style of modern C++. So it's intended as a kind of replacement for C++. On the other hand, unlike C++, which is an unsafe programming language, which lets you write programs that do arbitrary things, Rust comes equipped, or is claimed to come equipped with strong safety guarantees, including type safety and memory safety, and things like freedom from data races or thread safety as well. So it comes with even stronger safety guarantees than most safe higher level programming languages provide. Third, it actually, although it's not what I would think of as a functional language exactly in the traditional sense, it does have a lot of the features that are associated traditionally with functional languages. So it's, in some sense, a modern language, right? It incorporates a lot of ideas from previous languages, including things like algebraic data types and polymorphism. It has a mechanism called traits, which is very similar to type classes in Haskell. It has higher order functions, et cetera. So it really is, it includes a lot of the paradigms that you have in functional programming, even if you tend to use Rust in a lower level way. And then last but not least, it's actually, it comes with industrial development and backing, which is really important for a language to gain mainstream adoption. It's supported actively by a team of researchers at Mozilla, and there's many, many contributors from other people working at other big companies as well. So what actually makes Rust work? So I'm gonna expound about these 2 points throughout the talk, but I just wanted to sort of give them up front. One is that, as Xavier mentioned, it has a very sophisticated type system, what's called an ownership type system. And this is a very different kind of type system, as you'll see, has a different character than most type systems in other practical programming languages. This type system is used to somehow get this balance of the low-level control on the one hand and strong safety guarantees on the other. At the same time, although it has this very strong type system, there's an awareness within the Rust community that not all programs will be able to fit in this type system. Not all programs will be able to type check. And this is just a fact of life. And so there's an embrace within the Rust community of the idea that some pieces of code, some very difficult pieces of code, some tricky bits of low-level code will have to be written in an unsafe fragment of the language. And that this is okay as long as these bits of code are safely encapsulated behind interfaces. And so this idea existed before. I mean, there are other languages, many other languages that provide unsafe escape hatches, but Rust really takes this to a different degree. And what I'm going to talk about today is a large part of it is how we can make sense of this interaction between safe programming, or a safe type system, and bits of encapsulated unsafe code. How can we give a foundation for understanding why that's a good language design? Okay, so, right, and just to say, so this is, in some sense, the goal of the Rust Belt project, which is this ERC project that we've had going on for the past 5 years, is to build the first formal foundations for this language. This is really the first big project to study Rust. And so what I'm going to talk about today is not the end point. It's not the final story. It's just the beginning. So I'm going to talk about, I'm going to, actually, the first part of the talk, I'm going to give you a sort of a background on what Rust is, sort of a little tutorial. And then I'll talk about 2 pieces of work that we've done that are the core of the Rust Belt project so far. One of them is about understanding the language, so trying to build a soundness proof for Rust that encompasses, that accounts for the way that Rust programs are actually written, which is in this combination of code that is well typed according to this sophisticated type system, as well as libraries that make use of sort of judicious use of unsafe code. And the second part will be about some work we've done very recently on evolving the language. So we're actually trying to help define an operational semantics for Rust that would allow us to justify very aggressive optimization, type-based optimizations that the Rust developers want to be able to perform. So this is a place where we're actually really giving back to the Rust design and hopefully influencing it in a positive way. So, but first, before I do either of those, oh, right, and as I said already, the key challenge in both of these points is understanding this interaction of safe and unsafe code, which is, I think, a unique design point of the Rust language. So, so the first thing is going to be understanding Rust, and to do that, I have to give you some basic background on what Rust is. So, the sort of the basic idea of the Rust type system is that the root of all evil in systems programming, the cause of all sorts of, the reason that programming in languages like C and C++ is can be such a disaster, is the unrestricted combination of mutation and aliasing. In other words, when you have an object where you have a reference to an object, and then some other part of the program manipulates that object through a different reference, another alias, and perhaps mutates it, maybe deallocates the object, reallocates the object, somehow corrupts your view of the object. This can lead to all sorts of problems, such as dangling pointers, use after free errors, iterator invalidation, data races. These are all caused by this combination of mutation and aliasing. And the idea of the Rust type system is to prevent this by not allowing an object to be both mutable and aliased at the same time. Okay? So there are mechanisms in place that allow an object to be either mutable or aliased, and even to go back and forth between these two things, but not to have both at the same time. So then let's see how this actually plays out concretely. So here's a simple example. And I should say that so the idea of how you enforce this in the type system is through this concept of ownership, which we'll see here. So, so here we have a vector that we created. This is a mutable vector v. Initially has the contents 1, 2, 3. We push 4 onto the end of the vector. Okay? And then here we send the vector to another thread. Okay? We call the send function and pass it the vector v. And once we've done that, so you see that's the type of send over there. It takes a vector as an argument, and once you've done that, you've transferred ownership of this vector away to the other thread. Okay? So consequently, if you try to use v again by pushing to it, okay, you'll get a type error which says that v has been moved. And this is a really good thing because once you've sent that v to another thread, it's perfectly possible for that thread thinks that it has access to the vector. It could be simultaneously trying to mutate it as well, and then you would have what's called a data race, where you have two accesses to some object, some shared object, at least one of which is a write. In this case, it could be both of them are writes, and where there's no synchronization between them. Okay, and this can lead to, according to the semantics of a language like C, this could lead to, or Rust, this could lead to undefined behavior of your program. So in Rust, this is prevented entirely using by the type system, which says you're not allowed to do that. Once you've sent v away, you no longer have ownership of it, and so you're not allowed to access it anymore. Okay, so popping up, the idea is that if you have access to some variable in your scope, in this case we had access originally to the variable v of some type t, then this expresses not only that you're allowed to use it, but that you own that object. You know that there's no other piece of the program that can access that at the same time. So that means you can mutate it as much as you want because you know that there's no fear of any aliasing, and also you're allowed to deallocate it. And in fact, if you own an object and then that object goes out of scope, it will automatically be deallocated by the Rust compiler. So one thing you might wonder here, if you're paying very close attention, is when we called the push method on v, that's basically calling a push function and passing it v as an argument. So when we passed that v as an argument, why didn't it get moved at that point? Why were we still allowed to refer to it in the next line when we sent it? So the answer is that actually this is syntactic sugar. So really what's happening here is that you're not actually passing v as an argument to the push function from the vec data type. You're actually passing a reference to v. Okay? And this is where we get into the second key mechanism of Rust, which is this idea of references and borrowing. So the idea is that when we pass v to the push method, we're not actually passing ownership. We're just giving it temporary ownership. We do need to give it some kind of ownership because it's going to be mutating v. But we're not giving it full ownership. We're not sort of just giving v away. We're giving it where it's called borrowing v. Right? Push is borrowing v for the duration of the call, of the function call. And this is done by creating a reference. So we write this ampersand mute v, which says we're creating a mutable reference to v, which is then passed to push. And that means that this is basically passed by reference versus passed by value. When you pass by reference here, in this case, push is just borrowing that temporarily, and it gives back ownership at the end of the call to push. Okay? Whereas when we passed v by value to send, that was moving ownership away permanently. Now, how is this reflected, just to be clear, how is this reflected in the type of push? You see the type of push does not take a vec as an argument, it takes an ampersand mute vec. And actually, to be more precise, it takes an ampersand tick a mute vec. So this looks like a mouthful. What is this tick a? Tick a here is what's called a lifetime. So the lifetime is basically something that's inferred by the Rust compiler. It tries to figure out what is the minimal lifetime that it can pick for this borrow of the vector. Right? And it sees that actually it only needs to, according to the type of push, push only needs to borrow this vector for the duration of the function call, and it can figure out that after the function call, the original our code should get back full ownership of the vector. Okay. By the way, I should say, if anyone has any questions or get very confused during this presentation, feel free to just raise your hand. I'm happy to answer questions during the talk. So to summarize this point, right? So &mute x now is a way of creating a mutable reference to an object. And the idea is that this gives you temporary ownership, borrowed ownership of the object, which lasts for the duration of some lifetime, written tick A, which is something that's inferred by the compiler. When you have a mutable reference and the lifetime of that reference is ongoing, then you can mutate the object as you wish. You know that there's no other aliasing to the object, but you do know that after the lifetime is over, you have to give you can't touch the object anymore. Okay. So we saw fully owned objects, mutable references. A third thing is shared references. Okay. So here's an example. Here's a very simple example of where you want to allow aliasing. Right. So with full ownership and mutable references, you have mutation but no aliasing. With shared references, you have aliasing but no mutation. So here's an example where we have some variable x, and we want to share access to this variable between two threads. And this is done here using the join function from the rayon library. So this is basically this is a simple example. We're just reading the value of x in these two threads. Okay. And we see that we wrote &x there to indicate that each of these threads has taken a shared reference to this object. And so there's a couple things to notice here, right? So the first thing is, so this is when you write &x, this creates a shared reference of type &kt, so there's no mute, so that means this is a shared reference. Again, the ownership is just borrowed for the duration of some lifetime, and again, the compiler figures out sort of the minimal lifetime that will encompass the uses of that shared reference. In this case, that minimal lifetime is the duration of the join. So this join just means you spawn these two threads, and when they're finished computing, then you continue. And this allows for these threads to access x at the same time, because that's perfectly fine as long as they're just reading x, they're not mutating it. Good. And another thing you'll notice here is that after that lifetime is over, we are allowed to mutate x again, right? It figures out that the shared references only need this lifetime of the duration of the join, and after that we can mutate x again. It's perfectly fine. We have full ownership. So this is all inferred implicitly by the compiler. So summarizing this sort of very brief tutorial of Rust, it's all based. This type system is based on this idea of ownership and borrowing. You can have full ownership, then you can do whatever you want with the object because no one else can access it. You have mutable reference to an object, which is a temporarily owned reference, where you know that, again, there's no other aliases, so you can do whatever you want with it. Although not deallocated. Okay, when you have a mutable reference, you cannot deallocate, but you can do everything else. And with a shared reference, you can only read the object, but you can have multiple aliases and freely copy them. And this is all managed through this idea of lifetimes, which decide how long these borrows last. Okay, so that's a nice story. Unfortunately, it's missing there's something missing from this story. Okay, this is the story, by the way. If you hear a talk on Rust, you'll hear some story very much like this. But people often leave out the next slide. Okay, which is that this doesn't account for a lot of programming paradigms in low-level languages. There's a number of different kinds of data structures which do not fit into this somewhat restrictive story that I've told you. Okay? Because sometimes you need to have the ability to mutate some state which is aliased. There's no way around it. Okay? For example, when you're implementing certain kinds of pointer-based data structures, like a doubly linked list, there's no way around mutating alias state. It's fundamentally, there's a bunch of mutual references to objects, and you want to be able to mutate them. If you're implementing a synchronization mechanism like locks or channels or semaphores, the way you implement this communication at some point at some level of abstraction is going to be to mutate some shared state. If you want to implement memory management abstractions, which in Rust, for example, there's a reference counting. Reference counting is provided as an abstract type that you can wrap around any object. That reference counting is going to be implemented through mutation of this shared reference count. So at some level, you need alias mutable state. And the question is, what do you do about it? So in Rust, the way this works is that these kinds of abstractions are provided by libraries. Right? They're not really allowed in the core type system, but they are provided by these libraries, which you can think of as extensions to the safe language. And I'll give you a simple example of that. So here's a mutex library. So mutex is implementing sort of a lock that wraps an object. So if I in the beginning here, I wrap this integer 1 with a mutex, and that means the only way to access this integer the only way to gain access to this integer is through acquiring a lock that's associated with this mutex, and then you will be able to mutate the underlying integer. And here, what I've done here is I have, again, something like the join example from before. I have shared references to this mutex m, except now, instead of just reading the shared thing, we're actually going to mutate it by first acquiring a lock. So you see this where we call, this point here where we acquire the lock method. Where we call the lock method. We get effectively a mutable access to the underlying integer, and then we can mutate it. And then at the very end, we can cast aside the mutex, because at the end we have full ownership of the mutex. We could just get back full ownership of the underlying integer. So so this is interesting. Because this is basically giving us a shared mutable state. All right? So just to show you a little bit more about the type of this lock function that's going on here, it's taking a shared reference to the mutex, and then it's giving us back this complicated looking thing. Okay, so let's, I'm going to simplify this for purposes of presentation. Instead of lock result mutex guard, that's basically a fancy way, modulo error handling, of saying you have an ampersand mute. Okay? So effectively, it takes a shared reference to a mutex, one of these sort of read-only references, and gives you a mutable reference to the underlying data. Right? So that looks funny, right? Because I thought, I just explained that when you have a shared reference, you can only read through that. You can't mutate. And indeed, this is a phenomenon that you get with these libraries, like mutex, which in the Rust lingo is called interior mutability. This means you have a shared reference. Through a shared reference, you can gain mutable access, or you can do some mutation on the underlying object. And so, the natural question is like, what's going on? Okay, like, I just told this story about how aliasing and mutation, this is a terrible thing, you shouldn't combine them, and yet that's exactly what's happening here, right? You have alias references, and you're allowed to mutate through it. So what gives? Okay. Well, what gives is, of course, that you can't implement such a thing. So first of all, you clearly can't implement such a thing according to the rules of the Rust type system itself. So the implementation of this lock function uses what's called unsafe block. Okay, so this is the implementation of, or simplified implementation of the lock function. It calls the lock function from the pthreads library, and that is that has to be put inside an unsafe block, because now we're doing something that the Rust type system cannot verify as a safe operation. Okay, so basically, it's now the obligation is on the programmer to make sure that they're not screwing things up. And the idea is that although we're using this unsafe feature, right, calling out to this pthreads library, things are still okay. We haven't actually disturbed the safety of the language, because the interface that we provided to the clients of mutex is a safe interface. So in other words, so long as you're a client of this library and you just call the lock function, you just adhere to the API, and you're otherwise safe, you're otherwise adhering to the rules of the Rust type system, you shouldn't be able to get any bad behavior, because the whole point of the locking is that it is providing that synchronization. It's ensuring that only one thread will be mutating this shared data at a time, and that there's proper synchronization between those accesses. So you know that there will not be any data races when you use this library. That's the claim. Okay? And I should say, by the way, it's similar for join. Actually, the implementation of the join function that we saw earlier in several examples, that's also one of these examples of an API that's implemented internally using unsafe features, but provides this safe interface, so you should not be able to use that to break the language. So the natural question is, like, why does this work? Okay, so this was the original motivation for the Rust Belt project. We saw this and we thought, well, this seems interesting. There's this claim, non-obvious claim that Rust is safe, even though it's doing this funny mixture of this strong type system and these sort of encapsulated uses of unsafe code in the implementation of a number of core APIs. So basically the goal of this first part of the work that I'm talking about is to build a safety proof or a framework for proving safety of Rust that is extensible in the sense that when you when you develop a new library, if your library uses unsafe code internally, you have a way of establishing formally that it is not breaking the soundness of the whole language. Okay. So this is the work we published in Popl 18 initially, and then I'm going to talk about now on something called lambda Rust. So I'm not going to show you the full details of what we did. I'm going to sort of just give you an overview so that you get a rough idea of what this looks like and what the general methodology is. And I should say the first thing that we had to do before we could do any proving about anything was to formally define something, okay? Because Rust is not a formally defined language, right? Rust is a language that's been developed in practice. It has a compiler, and prior to our work, there was not really any work that attempted to formally define the language in such a way that you could even talk about the interaction between safe and unsafe code. So a big part of the initial work that we did was just trying to define what Rust is, or some abstraction of what Rust is. And that's what we called lambda Rust. So I'm not going to show you the full details of this, but I'll give you the rough idea. So we have a type, here's a syntax of types. In lambda Rust, we have a sort of standard types like bool and int. We have a bunch of pointer types. So the own type here corresponds to the box type in Rust, or in general to owned objects. So the idea is that own tau means you have a pointer to an object of type tau and you own both of them fully. And then the ampersand mute and ampersand share types, those correspond, as you would expect, to mutable and shared references. And then there's a bunch of other types I'm not going to go into the details of, but they correspond to the types you sort of expect to see in a modern language, including recursive types and sum types and product types. These are all sort of relatively standard by comparison. Then we have a typing contexts. So these in Rust are a little more complicated than in a traditional functional language because they assign types to paths. So you want to be able to say that a certain path into a structure has a certain type. And the path is basically, you can think of it as some projections from a variable. And the reason for this is simply that in Rust, I might have initially some access to some variable. I might give away ownership of some pieces of the structure that variable points to, and I still have ownership of the other pieces. So I have to have a somewhat more refined treatment of the ownership of parts of a struct. But this is a sort of detail. And then there's a bunch of typing judgments, and the key, these look a bit different than the typing judgments you may have seen in functional languages, because they're what's called substructural. Okay? In a structural typing judgment, once a variable has a certain type, it has that type forever. Okay? You don't lose the property that a value has a certain type. In a substructural language, or one of these ownership typing languages, whether a variable has a certain type or whether you're allowed to use a certain variable changes over time, as we saw in the very first example where we gave away ownership of that vector, right? We had it initially in our context. After we called send of x or send of v, we lost access to v, and so it's no longer in our context. So correspondingly, the typing judgments have this sort of stateful flavor. So you see here we have this judgment here, which says that if you can sort of ignore the details are not so important here, but basically E and L are these contexts that track information about the lifetimes. T1 is this typing context that tracks information about the paths that you're allowed to access. I is the instruction you're type checking. And then X here is the result of the instruction, the result value. It's a binder for the result value. And T2 describes what the typing context looks like after you've executed that instruction. So it may have modified, it may have removed some things from T1. It may have added some things. And then there's another judgment also for type checking whole functions, which does not have any result because we do the whole setup in what's called continuation passing style. Okay, but that's a somewhat of a technical detail. So there's lots of rules. Okay, I'm not gonna. Well, I think we should talk about that rule right there. No, I'm just kidding. So I'm not gonna go into great detail about these rules. You can read about some of them in the paper. We tried to actually get some significant coverage of a core of the language. This is not really the focus of what I want to talk about. What I want to talk about instead is how we. So once we have this basic setup of how you formalize the language, how do we prove soundness of it? Okay, so. So in his talk earlier this morning, Xavier talked about syntactic type soundness. otherwise frequently known now as the method of progress and preservation. So this is pretty much the standard approach that people have been using for quite some time, since at least the mid-late 90s, for proving safety properties like type safety and memory safety of programming languages, particularly typed programming languages. And the idea there is basically you take, well, you've already seen it this morning, so I'm not going to go into a great detail about that. But basically, you have some notion of syntactic typing. You can generalize that for a language for more realistic languages. You can generalize that to a notion of typing on machine states, and then you show that typing, well-typedness is preserved as the program executes. And as long as a machine state is well-typed, there's always, the next step of behavior is always well-defined. So this is what's nice about the syntactic method is that it's very simple and very generalizable to languages with a wide variety of features. The problem is it doesn't work at all for Rust, okay? Because it says nothing about unsafe code. Okay, so we get back to this sort of core theme of the talk, right? The interaction of safe and unsafe code. The method of progress and preservation assumes that your entire program is well typed according to a fixed set of typing rules, these syntactic typing rules. And if you have some piece of that program that is safe for some other reason, right? Like, we don't know yet, I haven't yet said what that reason is going to be, but for example, the implementation of the mutex API, right? That is not well typed according to any syntactic rules that I wrote down in those, on this slide here, okay? So if you have that kind of situation, then the syntactic type soundness approach simply is not going to work. And so, so what can we do instead? So instead, we use a method that's actually a very old method. It's been known in principle for a long time, but hasn't really been applied to languages like this, called semantic type soundness. And I'm going to tell you a bit about how this works, and more generally, it's known in the semantics literature as the method of logical relations. Okay, so here's logical relations in 4 easy steps. Okay, any child can do it. You first have to define a semantic interpretation of what your types mean. So the idea here is, instead of just saying the types are whatever the syntactic typing rules say they mean, we're actually going to define the meaning of types in some larger logic, right? So we're going to give some deeper understanding to what types are supposed to imply about their inhabitants. We're then going to lift that notion of typing to typing judgments, so we give a semantic interpretation of what the typing judgments mean. We then prove what are called compatibility lemmas, which basically show that our semantic model of types is compatible with the syntactic typing rules of the language. That doesn't make any sense. It'll make sense in a few minutes. And then we profit. Okay, so we'll see what profit means. But okay. So the first step is defining the semantic model of what types are, okay? So the idea is roughly, we want to say, like logically, what does it mean to have an object of a certain type? What does that tell us? So it's actually going to be a predicate. For every type tau, we're going to define an ownership predicate, tau.own, which is, for the details here are not so important, it's actually predicated over 2 things. You need to know what the thread ID is, of the thread that's owning the data, and you may have a sequence of values that are representing this object in memory. And then you want to say, do those sequence of values represent a value of an object of this type tau? And in addition, we need to somehow talk about this. We need to somehow get to this idea of ownership. So what does it mean that I own this object and no other piece of the program can access it? So actually, I know that Xavier talked about a logic in which we can talk about things like ownership about a month ago. I don't know if anyone was here. Does anyone remember what that logic might be? Yeah, this is a cheap separation logic. Oh yeah, well, so yeah, which logic should we use to assert ownership? Yes, separation logic. So, so separation logic is my favorite logic. Okay, so so separation logic is, for those who don't know, is an extension of Hoare logic that was developed about 20 years ago by a number of people, but including Peter O'Hearn and John Reynolds, Hong-Suk Yang, and others. And it's basically it was intended as a program logic for reasoning modularly about pointer manipulating programs, okay, which is the kind of programs we're also concerned with here. It's had a major influence on many verification and analysis tools. I won't go into details about that. But the key thing is that what makes separation logic really appropriate for modeling the type system of Rust is that it's essentially ownership logic. In fact, personally, I think a better name for the logic would have been ownership logic, because separation sounds kind of negative, right? I don't know, that's not, but ownership sounds, well, to some people at least sounds positive. So it's exactly about, it's a logic in which assertions talk about ownership of resources. That's built into the logic as a primitive notion. So in particular, so we'll see an example of this in a second, we're actually using a modern higher order concurrent framework for doing separation logic proofs, which we've been developing over a number of years, called Iris. I'm not actually going to go into great details about Iris in this talk, but I will show some examples of the power of Iris. The nice things about Iris from the point of view of modeling Rust are that it's A, implemented in the Coq proof assistant, and B, it's designed to derive new reasoning principles about new interesting application domains within the logic. Okay, so it gives you a way of extending the power of your logic without actually adding any new axioms. Again, I'll show you an example of this shortly. So I punted on the question of exactly how we define these ownership predicates, but the point is we're going to define them by within this Iris separation logic, and I'll get back to that in a minute. We then, once we've done that, it's very straightforward to lift to a notion of semantic contexts. So here you see that the way we model a context, for example, with two elements in it, this one path, P1 tau1 and P2 tau2, is we say that, well, P1 actually, we know that P1 owns tau1, or describes ownership of tau1, and we have an assertion here describing that we have ownership of tau2 through P2, and the key thing is this star, this is the separating conjunction connective of separation logic, which asserts that these two things are disjointly owned. So this is, the idea here is, for example, P1 might be one variable in your context, x. So it could be x is of type vec_t, and y is of type vec_t. And because this is the model of the typing context, we know that those must be disjoint vectors. They must be separately owned. Okay? So we could, for example, send x to one thread and send y to another thread, and these would not be conflicting at all. Okay? So this is an example where we're fundamentally making direct use of separation logic. And once we've done that, we can lift to semantic typing judgments. So we can say we want to model, so we want to interpret what does it mean for I to go from typing context T1 to typing context T2. And the idea is we just model this as a Hoare triple. Okay? Separation logic gives us Hoare triples, so we can talk about pre and post conditions. And we can say that, well, we have ownership of T1 in the precondition, and we have ownership of T2 in the post condition. So this is really just embedding the meaning of types in this Hoare logic, or the separation logic. And a crucial point here is that by doing so, we can leverage the fact that the separation logic already gives us safety for free. So the meaning of Hoare triples in Iris implies that if you can prove this, then you know that actually, as long as the precondition is satisfied, I is safe to execute, meaning it will have no undefined behavior. Okay. Moving on to point 3, compatibility lemmas. Right. So the idea is very simple here. We've defined this semantic model of typing. We now need to actually connect it up with the syntactic typing rules of the language. And the way we do this is, it's a very straightforward methodology. We just say, for every syntactic typing rule, and these are just two examples of syntactic typing rules, which I've written with these single turnstiles, we're going to change them to double turnstiles. And voila, okay. So what that means is, all right, when you had some typing rules before, which previously they defined what programs were syntactically well typed, now these become just lemmas that you prove about your semantic model. So we now have to prove for each of these rules that the premises imply the conclusion, okay? And that's it. And once we've done that, one corollary we get immediately is the usual syntactic notion of safety, meaning that if a program is syntactically well-typed, well, then clearly it's also semantically well-typed, because you can just do a simple induction on typing derivations. And then because, as I said, the semantic typing derivation the semantic typing judgment is safe by construction, you know that, well, syntactically well-typed programs can't go wrong. They must be safe to execute. They don't have things like data races or invalid memory accesses. But that's not the main point of, that's a good thing to know. But the main point of using the semantic model is we can go further. We can profit in the sense that we have a framework for talking about linking syntactically well-typed code, code that's in a safe fragment of rest, with code that's not, okay, with unsafe code. So here's a sort of pictorial version of that. So the idea is that here we have a typing derivation of some program which uses the mutex API. Okay? So there's a bunch of pieces of this that are syntactically well-typed. You see on the left. And then the problem is that any code that uses the mutex API is not syntactically well-typed. It's going outside the safe fragment of the language. So according to, as this is what I was saying before, according to the syntactic type soundness, the program, you can't say anything about this program. But now with the semantic model, we can, and we do, prove that mutex inhabits the semantic model of its interface. So we show that mutex is, in fact, semantically well-typed. And therefore, because we have these compatibility lemmas that we've proven, we know that we can link those semantically well-typed pieces together with syntactically well-typed pieces, and the whole program will be semantically well-typed and therefore safe to execute. So the slogan is, the whole program is safe if the pieces, the unsafe pieces, the pieces that use unsafe features, are semantically safe. Any questions about that? Okay. So I'm going to in the interest of time, I'm going to be brief. I'm going to sort of go pretty quickly through how we actually define this kind of ownership predicates, just to give you a little flavor of this. So the idea is, so I'm going to show a couple examples. So first, the own type. So this own type, remember, own tau means that we have a pointer to an object of type tau, and we fully own both of them. So correspondingly, I'm not going to go through all the details here, but the point is that the v here, right, has to be a location in memory, because that's the inhabitant of the own of this thing. It's a pointer, so v is some location L, and L points to W, so this is the points to predicate of separation logic, if you've seen that before. So we own that location L, and we know that it points to some value W, and that value W represents ownership of the underlying object of type tau. So this is just referring recursively to the ownership predicate of tau. Okay? And that's it. This is very bog standard separation logic. So what's not bog standard separation logic is this one. Okay, so this is the model of mutable reference types. So here, the first thing to note is this looks very similar to the model of fully owned types. The difference is, okay, so you can see inside, the orange parts are the same. The difference is this thing, okay. So this ampersand full kappa, okay, this is not a standard separation logic connective. So this is something where we're actually exploiting the fact that we're working in this very rich separation logic framework called Iris, where we can define new kinds of separation logic connectives and give them models and prove that the rules about them are sound. And so I'm just going to very briefly tell you the idea of this lifetime logic. The idea is essentially, and this is the bumper sticker version, is that traditionally when you talk about P star Q in separation logic, it has this idea of P is describing ownership of some piece of memory, Q is describing ownership of some other piece of memory, and those are disjoint pieces of memory, so they can be manipulated independently. With the lifetime logic, we're going to additionally have a way of splitting up ownership not just in space, but in time. Okay? So in particular, we have a rule like the following one, where you say, if you own some resource described by the assertion P, you can split it up into ownership of P for the duration of the lifetime kappa, and ownership of P afterwards. So that's what we see there's the period when kappa is alive, and then there's the period after kappa is dead. Okay? And so the first one, ampersand full of P, says ampersand full kappa of P describes access to P, or temporary ownership of P while the lifetime kappa is alive. And then this other thing on the right, which I'm not going to go into in detail, talks about ownership of P, or the ability to regain ownership of P once kappa has ended. Okay? And because you can't be both alive and dead at the same time, well, at least generally speaking, this is a safe thing to do. This is a safe form of separation. Okay? And so that's just like that's the very short version, but this gives you the idea that this is a non-standard notion of separation, but we can prove that this kind of a reasoning principle is actually sound within the Iris logic, and we've done that all in Coq. Okay, so I'm not going to talk about this in the interest of time. There's a lot of other details in the paper. We've proven safety of a number of interesting libraries. We've scaled, in more recent work, we've scaled our initial verification from a simple sequentially consistent model of concurrency that we started with to a much more realistic one using relaxed memory models. There's still a bunch of work, interesting work left to do. And if you want to ask about that at the end, I'll be happy to answer questions. So, to summarize, logical relations are really the tool of choice if you want to prove safety of languages where some pieces of the program may use unsafe operations. And although in the past this was considered a kind of difficult or complicated method, I would say that the advances in separation logic over the past 10 years, as embodied in something like the IRIS framework, this is now possible for a language even as sophisticated as Rust. Good. So that's understanding Rust. And so in the last part of the talk, I want to discuss sort of this more recent work that we've done on trying to evolve the language going forward. Okay? And for that, let's go back to this slide, right? So this is the high-level story about Rust. Right? The high-level story is of ownership. We have mutable references. We have shared references. No aliasing and mutation at the same time. And this is a nice story, right? This tells us that the reference types in Rust actually give us strong information about aliasing. And when your types give you strong information, it would be nice if your compiler could exploit that, right? So you'd like to, in general, when we have languages that are strongly typed, we can actually compile them more efficiently because the types give us more information statically, which you can use during compilation. And here, this extra aliasing information is another example of that. So let's see some examples of optimizations that should be enabled by this very strong type system. So here's this is an example of a function called test no alias. It takes two mutable references, x and y, as arguments. And it first mutates x to 42, and then it mutates y to 37, and then it reads x. Okay? And the idea is, according to the Rust type system, right, because x and y are mutable references, they're supposed to be unique. They should not be aliasing with any other references. So you should be able to deduce that actually when you read x at the end, it should read 42. It shouldn't have been overwritten by the write to y. So in particular, you should be able to optimize that. So you should be able to optimize that read and just return 42. More generally, if you call, instead of writing to y, if we just call some unknown function from some other part of the program, maybe some part of the program where we don't have access to the code, or some function that may have been passed in as an argument to our function, then we should also know that it could not possibly have mutated x because we have the only reference to x. So this is a point where you really have something, you really have a very strong property that you can't assume this in any other language, including any functional language that has manipulation of references. Right. So here's another example with shared references. So you have a function that takes a shared reference x and a mutable reference y. We read the value of x. We put it in the variable val. Then we write to y. And then we want to read x again. And we expect that x should be the same value it had, should have the same value it had before. And again, this must return true because x was a shared reference. It was read only. We know that there's no other parts of the program that should be writing to it. Okay? Again, more generally, you could replace that middle line with unknown function shared, right? We could actually, and this is the really cool part, you can pass x, this shared reference, to that unknown function, right? You're giving it away, and still you know when it comes back, it shouldn't have mutated x because you passed it a shared reference. There's no way it could have used that reference to mutate the variable, so you should be able to, again, do this optimization where we just replace, we don't have to read x afterwards. We know it's the same value as before, right? So the point here is these optimizations are really cool, okay? I mean, there's a separate question, by the way, and it's a very valid question of exactly how much performance can you get using these optimizations, right? This has not been tested yet, right? But this kind of optimization is like, the wildest, beyond the wildest dreams of a C compiler developer, right? This is an intra-procedural optimization that's based on this very strong information you're getting from the types. So this is something you could never do in almost any other language that I can think of. But there's a problem, okay? And if you've been paying attention at all in the first part of the talk, then you will not be surprised that the problem is unsafe code, okay? So what's the problem with unsafe code? Well, I'll show you. So basically the problem with unsafe code is unsafe code can do anything, right? So here's that test unique function that I showed you before, right? Which takes the mutable reference and then calls some unknown function. And I'm going to fill in the rest of the program and show you how, in fact, you could link this with some unknown function such that x will not, returning, at the end, we do not return 42. So here's I should walk through this in detail. So you have, at the beginning, we have some variable L, which is initially 13. And then we call the test unique function, so there you see L in the middle. We call the test unique function applying it to, or passing it a mutable reference to L, which is represented by X here. Okay, that's an alias to L, a pointer to L. So far, so good. But now let's do something evil. Okay, so suppose we start by creating a global variable alias, okay, which is a raw pointer. So what are raw pointers? I haven't really shown you this so far, but they show up a lot in unsafe code. They're kind of the dark evil twin to mutable references. Okay, so they're basically pointers about which no aliasing information is tracked. Okay, so you don't, and in fact, correspondingly, you can't use them in safe code. Okay, you can only access them or mutate them in unsafe code. So here we create at the beginning this alias pointer. We have this unsafe operation here, which assigns alias the address of this variable L. So now alias and X are both pointing to L. And now you can guess what's going to happen. Okay, we define this unknown function so that it updates through this alias pointer. Okay, it's going to set alias to the contents of alias to 7. And so that will effectively overwrite the thing that X is pointing to as well. So consequently, in the end, when we read X, we're going to get 7, not 42. Right? So clearly, this is very, very sad. Okay. What can you do about it? Well, one thing you could do is sort of throw in the towel and say, well, it was nice. We thought we could do those optimizations, but too bad. But that's not the approach that we're going to take. So instead, we want to say, well, it's not the optimization's fault that this rewriting of star x to 42 was not semantics preserving. It's the program's fault. This is a bad program. Even if you're using unsafe code, you shouldn't do things like this. All right? And then the question is, well, why not? Or what specifically is wrong with this program? So this is the goal of this work, is to actually give a formal semantics for explaining why this is a bad program. And for, in general, ruling out misbehaving programs that disrupt these nice optimizations that we'd like to be able to perform. So the idea is very simple. It's a well-known idea, which is to exploit undefined behavior. So we already seen in the first part of the talk, I didn't say explicitly about it, but Rust Rust has already a notion of undefined behavior. Things like when you have data races or you use a dangling or null pointer. And the point is that these things could happen in unsafe code, and it's the responsibility, it's a proof obligation on the part of the programmer to ensure that that doesn't happen when they use unsafe code. And if they screw that up, then the program can have undefined behavior. So if a programmer has some unsafe code that has a data race in it, the compiler is free to do whatever it wants on that program, right? It could turn everything into it can have arbitrary behavior, right? Anything is possible. Okay, so the point is, yes, there's this contract, right? The programmer is not supposed to do those things, and consequently, the compiler can rely on assuming that the programmer doesn't do those things when it justifies its optimizations. So the key here is just, we're going to make this undefined behavior, right? We're going to define a semantics such that this program has undefined behavior. And the way that we're going to do that is something we call stack borrows. Right? So the idea of stack borrows is very simple. At a high level, it's very simple. We're going to define an aliasing model. Okay. So what is an aliasing model as opposed to a memory model? You may have heard of a memory model. That's something that's something that defines which values you are allowed to read when you read from certain pointers. Right. What values you will get when you access a pointer. An aliasing model is somewhat different. It defines which pointers you're allowed to use in the first place, right? It says when you're allowed to use certain pointers to access memory. And we're going to define this aliasing model as part of an operational semantics for Rust that will ensure uniqueness of mutable references and immutability of shared references, thus enabling us to justify those optimizations that I talked about before. Once we've defined this thing, we have to show something about it. And basically the things we show are, number one, it's restrictive enough to enable useful optimizations. We've formally proven that the optimizations that I talked about before and a number of other ones are valid under the stack borrows semantics, under this enriched notion of undefined behavior. And then you also want to show that it's permissive enough to enable useful programming. So you want to make sure that you didn't make too many programs have undefined behavior, or else it's not useful for programmers. And to establish that, that's difficult to establish in a conclusive way. We've started to establish that by implementing the stack borrow semantics in an existing Rust interpreter called Miri, which is shipped as part of the Rust language. And we've checked the standard library test suite to ensure that it is conforming with with our stack borrow semantics and does not have undefined behavior. In fact, we were able to find a number of about 6 flaws in the existing Rust standard library, and those have been reported and fixed. So I'm going to just very briefly in the last 5 minutes talk to you about the details of how the stack borrows works. So the key idea is that Rust already has a way of ensuring these properties, immutability of shared references and uniqueness of mutable references, statically for safe code using what's called the borrow checker. This is the thing that implements these rules of the type system. But it only applies to safe code. And effectively what we're doing is turning this into a dynamic analysis that is checked alongside the execution of the program, and that extends the reach of those rules to also account for unsafe code. So this is easiest to show with an example. So here's an example where we have a mutable variable L, which is initially 13. We create a mutable reference A that's borrowing from L. And then we reborrow from A, so we create a mutable reference B that's borrowing again from A. We might access B, we might mutate it to 3. We might access A again, then mutate it to 4. But what happens if we try to mutate B again, we get a type error, okay? It will say that the lifetime of B is ended, so we can't access it anymore. So to understand why it's saying that, you have to understand the basic principles of the borrow checker. One of them is that when I lend you something, when I lend you a reference, I should not use it again until the lifetime of that reference has expired. Okay, so that means that when A is accessed in line 5, that must mean the lifetime of B is over. Okay, correspondingly, B, the recipient of a borrowed reference, should only use it while the lifetime is ongoing. So since the lifetime is over at line 5, when we try to use B again at line 6, that's a violation of point 2. Okay. So what do we learn from this? Well, we learn 2 things. One, borrows, as you execute a Rust program, the borrows form a chain. At any point in time, there's a chain of, there's the original owner, and then there was a borrow of that, and then there's a borrow of that, and there's a borrow of that, etc. Organized in a chain. And the accesses to things in this chain must be well bracketed, okay? Meaning, basically, you don't have an AB-AB pattern, which is, in fact, literally in this example is an AB-AB pattern, because I named them AB-AB. So you can only, that's not permitted. You may not be surprised to learn that you can understand this rule by saying the borrows have to be organized in a stack. Hence the name stack borrows. And so effectively what we do is we track alongside with every memory location a stack of aliases that can be used to access it. Okay? These aliases are represented by some tag, which is represented as just a natural number here. And so correspondingly, the memory is no longer just a map from locations to values or to bytes, but also a stack. So every location has one of these stacks of aliases. That's the first alias, that's the second alias. You can think of 1 here has borrowed from 0. Right. Reference tag 1 is borrowed from the reference tag 0. And then we have 2 rules about this. First, whenever you use a reference, there's an extra proof obligation, which is you have to make sure that that reference still is in the stack of the location you're accessing. Right? So the alias you're using is still a valid reference to that location. And secondly, when you use it, you pop any elements that are on top of your element in the stack, because those are no longer going to be allowed again. This was, as in the example with the AB-AB, when we have A, and then we have B, and then we use A again, we pop B off the stack. So then if we try to use B again, it's not going to be in the stack. So just to go back to this example and see why this is now undefined behavior, we had that the lifetime of alias began here when it borrowed from L, right? It was created as a borrow from L. Here, we created another borrow from L when we passed it to test unique, and that had the effect of removing alias from the stack. So now X has been put on the stack and alias has been removed. Consequently, when you try to access alias in the call to unknown function, it says alias is not in the stack, okay? And in fact, that's exactly, oh, sorry, I'm gonna skip over this part. Right. This is exactly the error that you get when you run this program in MIRI, the instrumented version of MIRI that we have. It will say something to the effect of, no item granting write access to the tag of alias, which is here called untagged, is found in the borrow stack. Okay? So it's saying exactly this error that alias is no longer in the stack. And that's why this program has undefined behavior, so we don't have to consider it when we're proving the validity of compiler optimizations. Okay, and as I said, we've implemented this in Rust. There's a lot of stuff I didn't talk about, but I've basically run out of time. So there's a lot of, I gave you the very short version of what's in the semantics. There's a number of other things we have to do to handle shared references, to handle data types with interior mutability, which we've already seen are these types where even though you have a shared reference, you can actually mutate the object. There's other mechanisms we have in place to enable further optimizations of moving writes around unknown code. And there's still future work to be done on extending our semantics to handle concurrency. And furthermore, integrating this whole approach of stack borrows into the thing I talked about in the first part of the talk, which is this safety framework, or this framework for proving safety of Rust programs. So yeah, to sum up, stack borrows is a dynamic model of Rust's reference checker that ensures soundness of these quite aggressive type-based optimizations, even in the presence of unsafe code, by ruling out some additional uses of unsafe code as having undefined behavior. And you can try this out for yourself. So if you like playing around with Rust, our implementation of stack borrows is integrated into the MIRI, which comes with Rust. And so you can play with this, and you can read more about all this work that I've talked about and more on the Rust Belt website. And this is our Rust Belt team, and thank you very much for your attention.